Hello, the topic of today's lesson is kinematics. First, we'll briefly go over the theory, then see how it applies in practice. Through clear visual examples, we'll explore uniform at accelerated motion, motion on an inclined plane, projectile motion, free fall, and object launch at an angle to the horizontal. If the theory seems complicated, don't worry. Once you see it in action, it will become much clearer. You can always go back and review the explanation. Feel free to take notes if needed. Let's get started.
Kinematics studies the motion of objects without considering the causes of that motion. Mechanical motion is the change in an object's position over time. Since we live in a three-dimensional space, we describe an object's position using three coordinates. The coordinate system and the momentum we start measuring time from are called the frame of reference. In many cases, the size of an object is small compared to the distance it moves. So we simplify the object to a point mass. In kinematics, we study such objects and call them material points. The trajectory of motion is the path an object follows as it moves. The distance, or path length, is the total length of this trajectory. Distance is a scalar quantity, meaning it only has a numerical value. Displacement, on the other hand, is a vector. It has both magnitude and direction. Displacement is a straight line vector, connecting the initial and final position of an object. However, it's often more convenient to work with coordinates instead of vectors. In this case, we analyze motion separately along each axis. To describe motion, we need velocity and acceleration. Velocity tells us how fast an object's coordinates change. Acceleration tells us how fast the velocity changes. Both velocity and acceleration are vectors, but since we analyze motion separately along each axis, we'll use the projections of these vectors onto the coordinate axis. Now let's take a look at the equations of motion. The two simplest types of motion are uniform motion and uniformly accelerated motion. In uniform motion, velocity is constant, and position changes linearly over time. In uniformly accelerated motion, acceleration is constant, and velocity changes linearly over time. Here, x0 is the initial position of the object, t is time, and vx is the velocity component along the axis. The position follows a quadratic law. Here, v0x and ax are the components of the initial velocity and acceleration. Remember, motion along each axis can be analyzed separately. These equations are written for the x-axis, but similar equations apply to any other axis. Now let's see how to use these equations in practice. Let's start with the simplest type of motion, uniform rectilinear motion. We place the origin of the coordinate system at this point. Time measurement begins when the object is at the origin. We direct the x-axis along the direction of motion. The equation for uniform motion has the following form. In our chosen coordinate system, the initial position is 0. The velocity's vector is directed along the x-axis, so its projection is equal to its magnitude. In this case, the object moves 1 meter per second. That means its velocity is 1 meter per second. So the equation of motion takes this form. We can also represent this equation graphically. Since the velocity's projection is constant, the graph of velocity versus time is a horizontal line. The graph of position versus time is a linear function. To better understand how to use coordinate representation and motion equations, let's analyze the same motion in a different coordinate system. Now we set the origin at this position. We direct the axis opposite to the direction of motion. At the initial moment, the distance from the origin to the object is 4 meters. So the initial position is 4 meters. The velocity is still 1 meter per second, but now it's directed opposite to the axis. That means the velocity projection is negative, equal to -1. In this case, the equation of motion takes this form. Graphically, the velocity and position versus time can be represented as follows. Now let's move on to uniformly accelerated motion. The simplest example of such motion is free fall. We start measuring time from the moment the object begins to fall. The origin of the coordinate system is set at the position where the object is at that moment. The y-axis is directed downward. The equation for uniformly accelerated motion are as follows. The acceleration due to gravity is 9.81 meters per second squared, which is approximately 10. The initial velocity of the object is 0, and the initial position is also 0. With these conditions, the equation of motion can be rewritten accordingly. Let's represent these equations graphically. The velocity graph is a linear function, while the position graph is a parabola. Notice that the total fall time is exactly 1 second. Let's determine the height from which the object fell. We can find this value from the graph. We see that after 1 second the position is 5 meters. This means the object fell from a height of 5 meters. We can also arrive at the same result using the equations. If we substitute 1 second into the motion equation, we also get 5 meters. Now let's analyze the same process in a different coordinate system. This time we set the origin at the floor level. The y-axis is now directed upward. I recommend pausing the video and trying to write the equations of motion in this frame of reference on your own. Then check your answer. In this system, the acceleration is directed opposite to the y-axis, so its projection is negative. However, its magnitude is still equal to g. The initial velocity is still 0, and the initial position is 5 meters. With these conditions, the equation of motion takes the following form. Graphically, they can be represented as follows. From the motion equations, we now see that after 1 second, the object's position is 0. Being able to write motion equations in any frame of reference is a crucial skill that will help you solve physics problems. The next example we will analyze is the motion of an object along an inclined plane. The ball is initially at a height of 2 meters. The length of the inclined plane is 4 meters. From this we can find the angle alpha between the inclined plane and the horizontal surface. The sine of this angle is equal to the ratio of the height to the length of the plane. In our case, the sine is 1/2, which means the angle is 30 degrees. We start measuring time from the moment the ball begins to move. We set the origin at the initial position of the ball. In motion problems, it's almost always convenient to align an axis along the direction of motion. So we direct the x-axis down the inclined plane. Those familiar with mechanics may know that in the absence of friction, the acceleration of an object moving down an incline can be determined as g sine alpha. The sine of 30 degrees is 1/2, and the acceleration due to gravity is approximately 10. So the object should move down the incline with an acceleration of 5. Why this happens will be explained in more detail in the dynamics lesson. For now, let's approach it from the opposite direction and determine this acceleration based on the motion itself. Now let's analyze the motion. The acceleration is constant. The initial velocity and initial position are both 0. This gives us the equation of motion. The graphs of velocity and position as functions of time are shown in the diagrams. We know that the total length of the incline is L, or 4 meters. The object rolls down the plane in 1.26 seconds. We can write the equation and solve for acceleration. The result is 5, which confirm our calculations. Now let's analyze the same motion in a different coordinate system. This time we place the origin at the floor level. The y-axis is directed vertically upward, and the x-axis is horizontal. This choice of coordinates is less convenient, but it will help you practice writing motion equations in arbitrary coordinate system and learn how to find vector projections. You can pause the video and try to write equations of motion yourself. The equations should express the coordinates and velocity projections on the chosen axis. The acceleration is directed along the inclined plane, and the plane forms an angle alpha with the horizontal. In this case, the x component of acceleration is a cosine alpha. The initial velocity is 0. The initial x coordinate is also 0. This gives us the motion equations along the x-axis. The y component of acceleration has a magnitude of a sine alpha, but it's directed opposite to the y-axis, so its projection is negative. The initial velocity is 0, and the initial y coordinate is equal to the height h. This gives us the motion equations along the y-axis. I suggest checking that these equations also lead to an acceleration of 5. We know that the object reaches the bottom in 1.26 seconds. This means that its y-coordinate is 0 at that moment. If we substitute this into the motion equation, we again obtain 5. The last example we will analyze is the motion of an object launched at an angle to the horizon. This is a common problem in physics, and in my opinion, it best demonstrates the application of motion equations. An object launched at an angle moves along a parabolic trajectory. We start measuring time from the moment the ball leaves the cannon. We place the origin at the launch point. The key values we need to calculate are the range and the maximum height. Acceleration is equal to the acceleration due to gravity and is directed downward. The initial velocity is 8 meters per second, launched at an angle of 60 degrees to the horizon. The x component of acceleration is 0. The x component of the initial velocity is v cosine alpha. The initial x coordinate is 0. Motion along the x-axis is uniform, so the motion equations can be rewritten accordingly. Acceleration is directed downward, so its y component is negative and equal to g. The y component of the initial velocity is v sine alpha. The initial y coordinate is 0. Motion along the y-axis is uniformly accelerated. Since the initial velocity is 8 meters per second and the angle is 60 degrees, the x component of velocity is 4 meters per second. This means that the horizontal coordinate is equal to 4 times time. The y component of the initial velocity is approximately 6.9 meters per second. This means that the motion equations take the following form. Let's represent these functions graphically. The horizontal velocity remains constant, so its graph is a horizontal line. The horizontal coordinate depends linearly on time. The vertical velocity projection decreases linearly over time. The vertical coordinate follows a parabolic curve. Notice that the object reaches its highest point when the vertical velocity projection is 0. From the graph, this happens at approximately 0.7 seconds, so the total flight time is 1.4 seconds. From the graph, we can also see that the maximum height is 2.4 meters and the range is 5.6 meters. Now let's calculate these values using the equations of motion. There are two ways to do this. The first method is to note that at the highest point the vertical velocity component is 0. I will denote this time as tau. We can write the equation and solve for tau. Since the parabolic trajectory is symmetric, the total flight time is twice the ascent time. The second method is to note that at the end of the trajectory the object's height is 0. This gives us another equation. Notice that this equation has two solutions. One solution corresponds to the launch point. We are interested in the second solution, which matches our previous result. To find the range, we substitute the total flight time into the equation for the horizontal coordinate. To find the maximum height, we substitute the ascent time into the equation for the vertical coordinate. Let's calculate these values by plugging the numbers into the formulas. The values matches the one we found graphically. So far, We have analyzed the motion from the moment the object was launched until it returned to the same height. In our case, the object continues moving until it reaches the ground. Let's extend our motion equations to include this and find the moment when the object hits the ground. We now place the origin directly below the launch point. In this case, the motion along the horizontal axis is described by the same equations. However, the initial vertical coordinate is not 0. It is equal to the initial height, which is 0.8 meters. With this adjustment, the equations of motion take the following form. To find the time when the object hits the ground, we set the vertical coordinate equal to 0. This gives us a quadratic equation. Solving it, we find the total flight time. In our case, the initial height is 0.8 meters, and the vertical component of the initial velocity is 6.9 meters per second. The solution to the equation are negative 0.1 and 1.5. This means the total flight time is 1.5 seconds. By substituting this value into equation for the horizontal coordinate, we can find the distance from the launch point to the landing point. The result is 6 meters. That's all for today. Thank you for watching. If you have any questions, feel free to leave them in the comments. I'll try to answer them. Don't forget to subscribe to the channel and leave a like. See you in the next video.